The topic today is optimization, right? And we are going to talk about the adjustment of the optimization of the deep learning model, right? Let's begin. As you can see from the last time, that we can create a model, we can create a deep learning neural network or just a neural network by using the sequential interface in Keras, right? And in that sequential interface we can add the layer, like the dense layer means that we are adding the fully connected, and this will make the model becomes feed forward model. What we are adding here is the dense layers of 64 elements, 64 node, with the uniform initializing kernel, meaning that the weight would be equal, and the input shape would be 10 for this case, and then adding the activation function at the end. And afterward we can specify the type of optimizer that we can use in this model, and that can be done by just specifying the name of the optimizer, and then the model would just use the algorithm would just use the default parameters for optimization. Or you can create an optimizer. For example, this one, it built an SGD just like what you implemented in your first assignment. The SGD, the stochastic gradient descent, with the learning rate of 0.01 and the decay of the learning rate of 10 to the -6 and momentum of 9. What are they? And there is this Nesterov criteria as well. And then we use this SGD object as an optimizer, right? And you can see that you can specify a lot of parameters to control how the model would learn. But in order to do so, you need to understand the basic concept of for each of these parameters, for each of these elements in the model, so that you will be able to initialize and optimizers and then utilize it with proper understanding. So in order to initialize an optimizer, you can initialize it as instantiated, mean creating an object, and then just put it into the model.compile, or you can call the name, just specify the name like below here, that I specified as SGD, and then it will use the default parameters for that. So you can choose from different choice of parameters, and this will change. This will change when the developer include more types, additional types of optimizer into the model. But let's take a look at each of these to understand how it works, so that once there is a modification or an additional adjustment to the model, to the algorithm, then you will know that the basis work like this. Then the addition should work somehow similar to what it already has. Okay, so what we will look at would be in this regard, right? Including the SGD, the stochastic gradient descent, which you have already implemented. So I suppose that you should understand how it works already. The Nesterov momentum. What does it mean by Nesterov? What is momentum? And the ADA, right? This is adaptive moment. This is adaptive gradient, and the rmsProp, the Adam and Nadam, Nesterov Adam. Let's take a look. First, start with the stochastic gradient descent. Okay, so in this lecture, there would be no coding at all, right? We just look at the algorithm. We will look at how different types of optimizer will result in, or would kind of utilize different strategy in changing parameters. Let's start with this one, stochastic gradient descent, SGD. This update at the iteration k. So we have what we need to have first is the learning rate and initial parameters, right? That were initialized before optimization. Then for why the stopping criteria is not met, meaning that why it's still working. Then for the stochastic gradient descent, you need to sample from the training set, right? Sample the mini batch of m examples, x1 to xm. These correspond to the vector y, right? Vector yi. Think of this as each feature, right? X1 to xm here, and each of these would correspond to each target. right? Each m example, right? Each of these would correspond to target in y. Then afterward, compute the gradient. Compute the gradient by derivative of the loss function, like what we have seen earlier, and and then use this to update, right? Add to the gradient, and then assign it to the gradient, and then for this gradient, apply it by adjusting the parameters to the opposite direction of the gradient based on certain epsilon, which is running rate. So in this case, you can see that the rate of change, the rate of learning, is fixed, right? And it depends solely on the gradient size, that on how this would approach the target. What does it mean? It means that if the gradient is large, you are far away from, or there is a large change, then the adjustment would be a large step. But if the gradient is small, say if you are close to the target already, or if you stuck at certain plateau of error rate of loss function, then the adjustment would be none, right? There might not be any adjustment at all, right? So here, this is like, if you take a look at the next slide here, for the gradient descent or the stochastic gradient descent, the solution would try to move to the final solution like this. But instead of having just this adjustment alone, you can add the momentum. You can add the momentum to the gradient. What does it mean by momentum? Just think about the physical momentum. We are talking about the time when you move forward and you cannot stop, right? That's momentum. And momentum can be a model in this regard as well, that you can think of the change that you want to adjust to the parameter, and then keep the momentum, keep the previous parameters, and then use it to kind of control on whether the gradient that really occur should just adjust from the previous parameters. So it would be more like the cost correction rather than the value itself. So if you take a look at this one, the new here is the this is SGD with momentum. Okay, we have this gradient, the old gradient that we have. But instead of plugging this into these parameters directly, right, we can subtract it out, right? Actually add it to the momentum. This momentum is controlled by alpha. Okay, alpha. Think of, so momentum is similar to exponential smoothing. Right? So it means that you are keeping part of the previous value. So that would make the situation like, suppose that alpha is a large value and now epsilon can be a smaller value. So the change in gradient would affect the direction rather than the direction of the momentum, rather than the value itself. And once you got this value, it will be used again in the subsequent iterations. Right. So that's why in SGD with momentum, you can think of gradient as this as the arrow here, that it kind of drive you toward the direction, but you kind of keep the momentum, and then it will kind of make the step larger at the beginning and smaller at the end, because you control the size of momentum there. So in the momentum parameters, you are essentially specify how much do you want to take the previous gradient value and use it to form the gradient. Okay, that means stochastic gradient descent with momentum is just like gradient descent, but it would have this velocity parameter instead of using gradient directly, right? Now we use the gradient to adjust the velocity with the parameter, momentum parameter alpha, and then the velocity is added into the parameters. Okay, so if you are familiar with exponential smoothing, the technique that you can smooth the curve, this is practically the same thing, because you can see that the gradient just work as adjustment to the velocity, and then we use the velocity to drive the change in the parameters instead. Okay, this is the concept of momentum in stochastic gradient descent, and you can see that in this simple implementation. Just specify the parameter, the alpha of momentum. It means how much you want to keep the previous value. Okay. Next is right. The next is also another type of momentum, which is called the Nesterov momentum. This concept was introduced in 2014. It's a variant of momentum algorithm for deep learning. It's inspired by Nesterov accelerated gradient method by Nesterov in 1983 in 2004. So so basically it is like this, but you may wonder, is it different between this one and the last one? If you look at the equations, look at this equation, 1 over m summation of the loss function of f xi parameter theta and y, right, and epsilon here. This is the gradient. Then add to this is adding, right, adding to the opposite direction of the gradient, right, to the previous gradient, to the previous value that you will use to update to the velocity. Then use the velocity to update. Now for the Nesterov method, if you look at the equation, you notice that there is only one part that differs from the previous one. That is, instead of having this as theta, right, we are calculating the gradient of theta of the current parameter. Instead of doing that, Nesterov momentum will evaluate the gradient after the current velocity is applied. Right? After the current velocity is applied, then it will use that to evaluate the gradient. Okay. So the difference would be that you need to evaluate the gradient of the next point before knowing whether you would jump to that point. So the idea of Nesterov is that first you need to make a big jump to the direction of previous accumulated gradient that you already have. Then measure the gradient. Right. Just doing it at the end. Then that means for the Nesterov momentum. You can the difference in terms of algorithm would be this. We need to apply the interim update. Right. Interim update, the lambda tilde comes from lambda plus it's just like, suppose we go into using the same direction, what would happen? Right? Just like if you would drive the car, right? In your mind, you may think that, okay, during your drive, during your control of the wheel, you will look forward, and then you can guess whether you are going straight to the direction or whether you kind of deviate from where you want to go. And that means you in your head you already calculate that you go to that direction and whether what direction that you should take next. Right? So the analogy is like that. So what we have here is to first apply to calculate the interim parameters. Doing the interim update, you have theta plus alpha, and then using the same direction, alpha and the new the velocity first. Once we are at this point, then we can calculate the gradient of that point. Okay, the gradient of that point. And then after we got the gradient of that point, we will know whether we should keep going or not. If the gradient of that point is small, if the gradient of that point still go forward, right? We can then add it to the old gradient. That means we should go further. If there is, you should still go into that direction. But suppose the gradient point into another direction directly, like point into the opposite direction, then you would have the gradient value here that move to the opposite direction, and it would slow down the velocity. Just like you see that if you go straight and you hit the block, and then you can take a break, because you know that if you go there will be problem. So this is similar to the analogy that I used there. It's just the evaluation of the next value, which can make the step larger or smaller depending on whether the next step is desirable or not. Okay, this is the Nesterov momentum, Nesterov criteria. And you can see that by doing this, we adjust the value of gradient directly depending on the types of momentum, whether it is the momentum at the current point, the normal momentum, or the Nesterov momentum that you are evaluating the momentum of the next point in this case. Okay, so for now, what we have covered here is already this momentum, this Nesterov criteria, and the running rate, right? The running rate of the similar normal gradient descent. Let's look for more. Okay. So for now, you can see that we can play with the momentum that keep the previous value, and then it evaluate and change the direction of movement of our parameter movements into the direction of the next step or the current steps, that not just depending on the gradient alone, but the general movement, the general momentum as well. Okay, but in order to make this story more interesting, you can see that from the previous algorithm here, what we are doing now is to adjust the gradient value, but still these parameters has not been dealt with, the epsilon, the running rate, because the running rate plays important role on whether the step should be large or should be small. Now we are just modifying it based on the general trend, but whether it should be large or small, it depends on the strategy. Right? This is like one of the most difficult hyperparameters to properly optimize, because it affects the overfitting, it affects the underfitting conditions, and it is quite sensitive to the result. I would say the result is quite sensitive to the learning rate that you choose. So sometimes we would just trying to find the best one, or for example, in optimization method like simulated annealing, like the annealing actually control the step size of the change. If at the beginning it allowed the steps to be random, and at the end it kind of narrowed down the steps so that it would just take to the gradient only. So it's just similar to the same thing on that, whether you should allow the exploration and narrow down the exploitation, and that depends on that. Now let's look at the certain strategies and algorithm that would be suitable in controlling the learning rate. The first one that we will look at is the ADA-grad. ADA-grad, sorry. Right, I'm back. Okay, where are we? Right, ADA-grad, right? ADA-grad adapt the learning rate. It will change the learning rate of the model by scaling it with a certain strategy, inversely proportional to the square root of the sum of all square value of gradient. I know it quite long here explanation, but it's quite straightforward. If so, what is this value? ADA-grad. ADA-grad would change the learning rate, and how would it change? It would scale the learning rate in the inversely proportional way to the square root of the sum of the gradient. basically square of the gradient, so magnitude of the gradient. That means if you have trained the model for quite a long time, the scaling parameters would be large, right? So the parameters with largest partial derivative of loss have corresponding to rapid decrease. Parameter with small partial derivative have small decrease. So in order to explain this in a simple term, the more you train, the smaller step that you get. Right? So at the beginning you get a large step, and then afterward you get smaller step. That's the adaptive gradient. Now let's look at how it works. Now we need to have this global learning rate at the beginning. This is epsilon here. We have parameters theta, and we have this small constant for numerical stability in terms of division. First, we need to initialize gradient. Gradient accumulation variable, right? This would be a variable that sum the previous gradient. This r equals 0. Then for each iterations, we will compute the gradient here, similar same old gradient, and then for this gradient we will add it to the accumulation, the r, right? Just add it to accumulation to get the magnitude, the size of it. Then from that we can use the gradient and use it to compute the actual adjustment that it should take, and this depends on the gradient multiplied with this. This is the new learning rate. It comes from epsilon divided by the square root of r. Okay, so that means at the beginning the step would be large because it would be just epsilon and delta. And afterward, you have accumulate gradient more and more. The step will be smaller. Right? So at the end, so this is how the eta grad work. Right? This is the adaptive gradient. Right? The gradient would be adaptively reduced as you increase the iteration. Okay. Right. Any question first for this one? The previous one, the previous algorithms are quite easy. The rmsProp and so on. And you have already implemented stochastic gradient descent in the first assignment. And you can see that, well, actually these algorithms are not that difficult, right? Fancy name like eta grad, but you can see that actually it's not that difficult. You just need to control the scale the grade, the learning rate, and that's it. Okay. Next, let's look at another one. Right, this is eta delta, which was proposed in order to address certain issue in eta grad. What is that? Eta grad is sensitive to initial condition. Well, don't all algorithm work like that. If you work on optimization, you will know that every optimization problems are sensitive to initial condition, mostly, except those of evolutionary computing, and sometimes it also depends on the location of initial condition as well. There are even research that dig deep into how to get proper initial seed position, and not tuning the seed value, but they are like, should it pick the one that already there, should it uniformly distribute to all of the space for finding solutions. There are many research that take a look into that, but well, eta grad has that problem. It has the solutions are sensitive to initial conditions. So if initial gradient are large, then learning rate will be low for the remaining of training. Okay, because if initial gradient is large, then it would scale it down, right, at the beginning, but you don't know, maybe you take one large step and it's not enough, like well, you want to go to say Chiang Mai, and then you drove to say Ayutthaya. That's already far, right? But if the car, like the vehicle, the car, let's say you use EV charging battery, allow you to only charge in the scale of reducing the size of the charge, the time you charge to that, you wouldn't reach Chiang Mai probably. Yeah, but yeah, that's one of the example there. So in that case, you need to have like a way to dealing with this problem. That suppose you have large gradient at the beginning, what to do, right? So they not we actually Sealer created eta delta to overcome this sensitivity to this, right, to avoid the decay of learning rate. How does it work, right? In his paper, you can find his paper here in ARXIV, eta delta and adaptive learning rate method. Right, so well, this is the algorithm. Let's dig in. We have decay rate, this rho, and a constant epsilon, initial parameter x1. We first need to initialize the accumulation variable, just like in undergrad, right? In accumulation variable, but this one is e of g square, gradient square, equals 0, and e of delta x square equals 0 as well. And then for each of iteration, I can loop over the for update. We have for t equal 1 to t, I perform this compute gradient gt, and next accumulate gradient. Right? This is the accumulation of the gradient, and is the same as the last one, right? No, it's not actually. This accumulation comes from the previous accumulation plus the gradient square, and you can see this rho and 1 minus rho and 1 minus rho. So there is a meaning for E here, right? In statistics, you know this function, this E function, as the expected value function or the mean function. Okay, so instead of accumulating the gradient starting from the beginning until the end, no, eta delta work differently. Eta delta would calculate the exponential smoothing, actually the expected value of the gradient, of the size of the gradient, which come from the previous one, the previous value, time rho plus 1 minus rho, right? This is like rho and 1 minus rho work as like the adjustment, the decay rate, how fast you want it to decay, right? Depending or in terms of exponential smoothing, it is just like how much do you want to take the previous value. Okay, and then after you get the accumulation of the gradient, or I would say the accumulation of the expected value of the gradient, and then you can compute the update, and the update come from the RMS of delta x at the time t minus 1, and the RMS of the GT. What is that? What is the RMS? The RMS is the root mean square. Okay, that means you need to take square root, right? This is root mean square of GT, square root, right? And then this EGT, which is already square value, and it's already mean because this is the expected value, so that's why it is the root mean square of the gradient, this value down here, and RMS of delta x as well, since we have to calculate it at the next step, right? So at the beginning it's 0, but we need to calculate it at the next step, and we need to take a look at that first, right? But in any case, just divide them. So this would be the gradient, this would be the value that you use to update the parameters, and then multiply it with GT. To think about it in a simpler term, right? Gradient, right? GT is gradient, so delta x is obviously gradient. But this gradient will be controlled by this. It will be controlled by the learning rate, and this learning rate come from the actual adjustment divided by the size of the gradient. Now you may wonder, then what would be the value of the adjustment? Let's take a look at the next slide. This expected value of the adjustment square come from the previous adjustment plus the delta x square, this value square. Okay, so if you look at this closely, you will see that this x, delta x, would contain the g square inside, gt square inside here, but it will be scaled with based on certain value here, and this would be the size of the change, the actual change that happened. So when you put it this, and usually the actual change would be smaller than the gradient, so it kind of reflects the learning rate there. Right? So it's just like the learning rate, and then this learning rate will change depending on the value of the size of delta x and the size of the gradient. Usually at the beginning, size of delta x will be large, so it will have larger gradient, and once it's kind of reach closer to the target, it will be smaller. Okay, so this is eta delta. So instead of having the value using the accumulation of the gradient of the entire run, it used the smooth value of the gradient, and then use it to scale and then compute the rate. Okay. Next one is the another family which was proposed by Hinton, Professor Hinton, in 2012. The algorithm is called the rmsProp algorithm. Is a modified eta grad perform better in the non-convex setting by changing the gradient accumulation into exponential moving average. Well, sounds like the previous one, right? This one also in 2012, eta delta, addressing the same problem. This one in 2012 as well. But focus on the non-convex function. Right? Convex function is a function that you can find like the bottom part. For non-convex, then it might not be that case. All right, let's look at the algorithm to understand it more. We have the global learning rate epsilon, decay rate rho, and initial parameter theta. And we also have this small constant to control, to make the number stable, not divide by 0. Then you first have this r equals 0 as an accumulation variable. And then for each iteration, sample the training set, and for example, the batch, calculate gradient, sample gradient, and then accumulate the square gradient. All right, this now become more interesting. You have r, rho r, 1 minus rho, and gradient square. It looks just like what I saw earlier. Well, they are like similar concept here. So you have r here, then you can divide it by this learning rate, right? And then multiply with g. Basically, they are same concept, right? rmsProp just use expected value instead of the accumulation. Right, just the same as the eta delta. Okay. rmsProp also has this Nesterov momentum, which, as you know, just need to have an interim update, and everything else is the same. Okay, you have interim update to have the and then calculate gradient based on that, accumulate gradient first, and then accumulate gradient first from the next step, and then use it to scale. Okay, and then adjust the momentum. Now we have both momentum and adaptive gradient altogether, and then add it to apply the update here. Okay, this is rmsProp, which you can think of it as an extension of AdaGrad. Okay, any question before we look at Adam and Nesterov Adam? So suppose you can see the points of each of these technique, right? Instead of having the fixed step size, now you can have the adaptive step size. Right? There are even students that work on the thesis with me to address this problem, to adaptively tune the step size, but we are trying to make it to increase the exploration of the space by controlling step size and the gradient. Okay. In any case, let's move on to the next one. Right. Next one, the next adjustment strategy is called Adam. This comes from the names adaptive moment. Interesting, right? That means the moment will now be adaptive rather than smooth. Okay, on the previous one, that's the momentum, right? Now we talk about adaptive moments. Comparing to the earlier algorithm, this is like the extension of the rmsProp. So first, in Adam, the momentum is incorporated directly to estimate the first order moment, and then it includes the bias to get to estimate. Secondly, Adam would include bias correction to the estimate first to the above to account for initialization at the origin. Just take a look at the next one. You can see that it includes the bias of the moment. Right? In terms of moment, it means just like in derivative, right? First derivative, second derivative. Okay, let's take a look at the algorithm. This will be a little bit longer than the earlier one. We first have this step size, epsilon, and the exponential decay for the moment estimates. This is row 1 and row 2. Row 1 and row 2, which need to be specified. The exponential decay rate of the moment. And the small constant for numerical stability first, and also parameters. First, we need to initialize the moment variable to both 0. Okay, now we have S as 0 and R as 0. These would be the first moment and the second moment, which will be used to calculate the gradient, the final gradient. Okay, now in time step 0 and then go on, we have this sampling of batch and compute the gradient normally. And then, right, next is the main the core of Adam. Next, we need to calculate the first moment. It's called the biased first moment. This biased first moment comes from, just take a look and you see something familiar. Right now we use S multiplied by rho plus 1 minus rho multiplied by G. So this is like exponential smoothing. That's why it's called exponential decay. Exponential decay of the first moment. This one is just like the momentum, right? The first order momentum. And you can guess. Second one is it's called bias because it's bias in terms of statistics. Like you have bias estimator and unbiased estimator. In terms of bias, like you need to, for example, when you calculate the variance, need to divide the square error with n minus 1. Why n minus 1? Because you already know you need to make correction. You already know one value. You already know the mean, and that means the value that you use in terms of the difference has the order one more than it should have. Right? That's why you divide by n minus 1 there, basically. So in this case, we have the first moment estimate, which is just the normal momentum. think of it as the expected value of the gradient. The second one, this one is the second moment, but when you look at it, it's just the g times g. This is the gradient square, just the magnitude of the gradient. So think about this as, well, it's called second moment because it has this square, and you are actually compute the expected value of the size of the gradient square. Then correct it with 1 minus rho 1 and 1 minus rho 2. These rho 1 and rho 2 are from the above here, right? And the same as this one. Okay, now you have this first moment and second moment. Okay, then the update comes from S, the above, right? This is the gradient. Well, to think about this in comparison to the previous algorithm. The gradient, the change must be the gradient, right? And we are playing with the learning rate. So this is the same old gradient, but it's a smooth version of the gradient, this S here. And down here, this square root R is actually, instead of using the accumulation, right, we are using the expected value of the second moment. Okay? Here. The expected value of the second moment to control the learning rate, and here's the normal learning rate, and then use it to adjust the parameters. Okay, yeah, that's the Adam algorithm. Is actually similar to rmsProp, except that you now have this accumulation or the expected value of the gradient square to control the size of the gradient. Okay. Adaptive, the Adam has this adaptive Nesterov condition, the Nesterov accelerated adaptive moment estimation. This was the paper by Dosat in 2016. This is implemented in Keras. When you use it, you just need to specify that you're going to use NADAM and specify parameters. So this is just like Adam, but evaluating, well, just Nesterov condition, evaluating the next step first and then use it to guess, right, to calculate gradient and use that to update the value, right? So you need to kind of adjust the parameter first and then calculate gradient, adjust parameter, calculate gradient, then calculating the moment, making correction, and then update the parameters. Right. So in terms of convergence, comparing all the algorithm, you can look at this. This will repeat itself for quite a while. You can see that the fastest one is the eta delta. It reached the solution quite fast. Well, similar, I would say similar direction with the rmsProp. The one that kind of go where it want to go is the green one and the purple one, which is the momentum based, and the Nesterov adaptive gradient. Okay, and SGD is the smallest. You can see that it's quite it's the slowest. It hasn't reached the solution yet, not even halfway. And the author just reached the solution there. Right. In terms of performance, well, it depends on the paper you read, but those that are comparable just are like the NADAM, right? Converge really fast. Adam, and then rmsProp, then it goes SGD is the top here. Okay, but it doesn't mean that the faster the better, though. Depends on the problem that you are handling. In any case, if you can see that instead of using just SGD, if you apply moment, if you apply the adaptive moment, it becomes faster because the learning rate now has been adjusted. right? And you can see that for the whole method that it has incorporated with that I have covered here. Mainly, all of these techniques dealt with learning rate, right? They just adjust learning rate to make the change of parameters become faster or smaller at a suitable time. Okay, so that means you need to choose the right optimizer. There's no consensus which one is better than which. The popular one and the simpler one is the SGD. Very simple. And actually, you can even implement the rest on your own. You can see that even for Adam, even for the rmsProp, the algorithms are not that difficult. You just need an accumulation parameters, and then you can just implement it on your own, right? So just try it out, and there's actually not one correct algorithm. As I said, some will accelerate you to the optimal solution faster than the other, but whether it will give you an overfitted or not doesn't depends on these optimizers. It's still there's still other technique that need to be considered in terms of overfitting, right? But in any case, you can see that selecting optimizer will affect the performance of the training, right? Whether it will be fast or slow, whether it will converge faster or slower. Okay. Right, and that's actually all for today, which I cover different algorithm that allow you to create an optimization object, right? Optimization model, create an optimizer that would optimize your deep learning model. Okay, so that's it for today. And the next time we'll start on different architecture so that you can have more assignment. But next week there's no class next week. We'll have a class a week after next week. Next week I mostly probably be busy with the preparing for the midterm or for the other classes. But we don't have that. Never mind. Don't forget to submit your assignment. Okay. Even though the deadline passed, just submit the work. I will check on that. Right. Any questions about the optimizers that we have covered today? If you want to read more about this, I recommend this book. It should be on the chapter. Let me check. Should be on the chapter 8 of this book, and it might have more that I have not covered, like the heuristic approach in deep learning. But well, I will leave that to you if you are interested in research in adaptive adjustment of the deep learning model. This would be the sources that you need to cover. Okay. Since if there's no question for today, that's it. I will upload I have already uploaded the video of previous section to YouTube. So supposedly I should be able to post it tonight. For this one, well, need to edit it first, and then I will work on that later on. Okay. So in any case, let's call it a night. See you guys next time. Next time is the week after the midterm, right? Take care. Bye.